and 201 values, right? But how many multiplications is actually needed? Only 3. How do we compute this? Well, just notice that this is A0, B0, plus, what do we have? X to the 100, and the coefficient is A0, B100, plus B0, A100, and then finally plus A100, B100, X to 100, sorry, 200. How do we find these guys with only 3 large number multiplications? Which multiplications do we perform actually?
A0, B0.
Exactly, we perform this multiplication and that multiplication, and to get this, we simply take A0 plus B0 times, A0 plus A100, B0 plus B100, and just notice that this is A0, B0 plus A100, B0 plus A0, B100 plus A100, B100, right? Now, because we have this and we have that, we can subtract this, and what is left is precisely what we need for here, right? So only 3 large number multiplications needed. Okay, let's see some divide and conquer. Well, what shall we do? Okay, so I put, actually my admin, I believe he already put it on the web, a bunch of midterm practice problems, and let's do a few of them. So let's do a bit of divide and conquer. So here is a very nice one. So what is the Fibonacci sequence? Fibonacci sequence is F0 is 0, F1 is 1, and then F of n is equal F of n minus 1 plus F of n minus 2 for n bigger or equal than 2. Right? And A part says, show that the following matrix, F of n plus 1, F of n, F of n, F of n minus 1 is equal to the following matrix 1, 1, 1, 0 to the power n. That's A. And B part, compute F of n in log 2 of n many steps. If you did it by brute force, in order to compute Fn, it looks as if you have to compute all of the values from F0 all the way to Fn, because you have this recurrence, right? But in fact, one can compute Fn in log 2 many steps. First of all, how do we prove A part? We won't bother. How do you prove A part?
Induction.
Just by induction, it's trivial, really. If it's true for n, you just write what is for n plus 1, you multiply this by another copy of this matrix and you get exactly the next one. How would you use A? So the hint is use A to compute Fn in log 2 of n many steps. What's the trick? How would you efficiently compute? Okay, without the, let's not do the eigenvalues here. That would be one way of doing it. You reduce this matrix to a canonical form, right, with just eigenvalues on the diagonal, and then, is this necessary? How would you compute the n power of a number? How many multiplications do you need to find the nth power of a number? Approximately how many multiplications? Using divide and conquer. How would you compute x to the 32? You start with x, and then you square it, and do you multiply it by x now? No, you square it again. So you get x to the 4th, then x to the 16th, and so forth, and finally x to the 32, just by squaring. So in order to compute a number on how many steps does it take? How many multiplications to compute n power of a number? What's the recurrence? It's about 2 times log n, right? Because depending, okay, let's see. What is the idea? The idea is that x to the 2n is x to the n squared. So this is just one extra multiplication. And x to the 2n plus 1 is equal x to the n squared, and then times x. And for this, we need 2 multiplications. So depending on what n looks like. So which n is the hardest to takes the most multiplication? So if you take how many multiplications you need depends on what n looks when you represent it in binary, right? Because for each 0, right, you have only 1 multiplication, and whenever you have 1 to do it recursively by this formula, you need 2 multiplications. So the toughest one would be 1, 1, 1, right, which is 2 to the k minus 1. Okay, but so how would you then compute f of n in log n many steps? Well, you do exactly the same for the matrix power, right? So you always compute n to the 2k is equal n to the k and then squared, and n to the 2k plus 1 is equal n to the k squared times m. So it will take you only log 2 approximately, not more than 2 times log n matrix multiplications, and each matrix multiplication involves how many 4, right, multiplications. So this will be altogether how many? About 8 log n matrix multiplications. And then once you get this matrix, well, you simply read out what's in this corner to get what Fn is. So interestingly, even though Fibonacci is defined by recursion, linear recursion, right? That looks as if you have to compute all the values from 0 to n. Actually, this shows that in fact Fibonacci numbers can be computed in logarithmic time. So, and on the meter, this was one here on the meter, if you have A and B, well, it's probably A has a purpose there to help you with the B. Okay. Is it clear how this works? Right, so the point is just computing the power of this matrix, but we use divide and conquer. We square wherever it's possible, or square and multiply with a single copy of n. Okay. So let's do another very pretty divide and conquer. You have a chessboard of size 2 to the k. Okay, so you have a chessboard of size 2 to the k. And it's missing a square. Okay? You have to cover this chessboard with dominoes that are 3 squares attached to each other like this. So this is. How would you solve this problem using divide and conquer? So you don't know where you do know where the hole is, but it can be at arbitrary location. Yes?
So if you divide it in 4 parts,
Excellent. So we divide it in 4 parts.
and then you can put the domino thingy, so that you have a missing spot in all the 4.
Ah,
So-
excellent. So the trick is put the domino exactly in the center, like this, so that now each of the 4 pieces has 1 missing field. And then recursively, we call our algorithm recursively on all 4 parts. You see, if we didn't do that, we cannot recurse. Because here you have 3 complete boards, and only 1 that has a hole. But if you put the domino in the center, right, now all you have to cover is 4 boards, each of them having, right, because these cells are already covered, you have to just cover the leftover, right? So for example, for this board, you have to cover this, and it's exactly a complete board with 1 missing field. Okay, that's a kind of sneaky one. So, but the idea is divide and conquer. Okay. So let's do a little bit of, well, it's time to make a break, and then we will do some more gritty algorithms. There will be no surprises on the midterm. So if you understand how you multiply polynomials, and if you understand basics, what FFT is, right? You split the polynomial, well, we will do a few examples. So, and gritty, everything will be highly doable.